Right now, as you read these words, light is traveling toward you from a star, not from some distant smudge at the edge of the observable universe, not from a galaxy so far away that the photons departing it predate the existence of Earth. This light left its source just 4 years and 4 months ago. In cosmic terms, that is nothing. That is the blink of an eye, in a universe that has been blinking for nearly 14 billion years. The light arrives at your retina, carrying information about a stellar furnace that burns at roughly the same temperature as our own sun, that possesses roughly the same mass, roughly the same color, roughly the same quiet, ancient fury. If you stepped outside tonight and faced the southern sky, you would see this star blazing near the foot of the constellation Centaurus. Brilliant, yellow-white, serene. That star is called Alpha Centauri A, and for longer than any living astronomer can remember, it has been keeping a secret. For decades, scientists have aimed the most sophisticated instruments ever constructed at this nearby stellar furnace, desperately searching for something orbiting it. Planets, worlds, any gravitationally bound companion massive enough to leave a trace in the light, a wobble in the star's motion, a faint shadow crossing its face. Generation after generation of astronomers devoted careers to this single question. They built better telescopes. They refined detection algorithms. They argued at conferences and wrote grant proposals and lost sleep over data that stubbornly refused to reveal what might be circling our nearest sun-like stellar neighbor. The results, decade after decade, were silence. Not the silence of certainty, the silence of instruments not yet good enough to hear. Then, in August of 2024, the James Webb Space Telescope pointed its golden mirrors toward Alpha Centauri and found something that made scientists stop breathing for a moment. A faint point of light, positioned roughly 2 astronomical units from the star, glowing in mid-infrared wavelengths consistent with a Saturn-mass world heated by the star beside it. The detection achieved a statistical significance of 5.5 sigma, meaning the probability of random noise producing such a strong signal, by pure chance, falls below 1 in 10 million. The object was designated S1. For a brief, extraordinary window of time, it appeared that humanity had finally answered the question that had haunted astronomy for 70 years. Then S1 vanished. Follow-up observations in February and April of 2025 revealed nothing. The planet, if it existed at all, had disappeared. The nearest sun-like star to Earth had shown astronomers something remarkable, and then taken it back, leaving a mystery that continues to puzzle researchers and challenge every assumption about what the most powerful space telescope ever built actually detected in the Alpha Centauri system. This is the story of that detection, of the extraordinary length scientists went to in order to achieve an observation that many considered impossible, of what they found when they finally succeeded, of why it disappeared, and of what its existence confirmed or otherwise would mean for our understanding of the cosmos and our place within it. If you find yourself moved by the idea that we might finally know what orbits the nearest star to our own sun, do something small for this channel, hit the like button and subscribe. It costs you nothing and helps this work reach the people it was made for. Now, make yourself comfortable. Let us begin. Alpha Centauri is not simply another star. Understanding why requires stepping back from the data for a moment and looking at the system the way a navigator might, orienting by what matters most rather than by what is merely measurable. The star sits 4.37 light-years from Earth. In absolute terms, this means that light traveling at approximately 186,000 miles per second requires 4 years and 4 months to cover the distance between us. A spacecraft moving at the speed of the Voyager 1 probe, currently the most distant human-made object in existence, at roughly 14 billion miles from the Sun, would require approximately 7,500 years to reach Alpha Centauri. A commercial airliner cruising at 600 miles per hour would take roughly 5 million years to complete the journey. The distance is staggering by any human measure, and yet in cosmic terms it is essentially nothing. Consider that the observable universe extends approximately 46 billion light-years in every direction. Consider that the Milky Way galaxy alone spans roughly 1,000,000 light years from edge to edge. Consider that the nearest large galaxy to our own, the Andromeda Galaxy, lies approximately 2.5 million light-years away. Against these scales, 4.37 light-years is less than a footstep across a continent. Alpha Centauri sits practically in our backyard. It is our neighbor, in the most literal sense that word can be applied to objects separated by trillions of miles. This proximity has made Alpha Centauri special in the human imagination for as long as we have understood what stars actually are. The system itself is not a single star, but a triple stellar family. The two brightest members, Alpha Centauri A and Alpha Centauri B, orbit each other in an elongated path that takes approximately 80 years to complete. At their closest approach, the two stars pass within roughly 11 astronomical units of each other, a distance slightly greater than the separation between our Sun and Saturn. At their most distant, they draw apart to approximately 36 astronomical units, comparable to the orbital radius of Neptune in our own solar system. Seen from Earth, the pair appears as a single brilliant point of light to the naked eye, only separating into two distinct stars through even a modest telescope. Alpha Centauri A, the focus of the story you are following now, is the dominant partner. Its mass exceeds our Sun's by approximately 10%. Its radius matches solar dimensions almost exactly. Its surface temperature of 5790 Kelvin falls within 200 degrees of our Sun's 5772 Kelvin photosphere. Its luminosity exceeds solar output by roughly 50%. In nearly every measurable characteristic, Alpha Centauri A is what astronomers call a solar analog, a star so similar to our Sun that you could mistake one for the other from a sufficient distance. Alpha Centauri B is smaller, cooler, and dimmer, an orange dwarf star containing roughly 90% of solar mass and emitting about half the Sun's luminosity. Its surface temperature of approximately 5260 Kelvin gives it a slightly warmer, more orange hue than its companion. In isolation, it would be a fascinating target for planet hunters. In conjunction with Alpha Centauri A, it creates observational complications that have frustrated astronomers for decades. Then there is the third member of the family, Proxima Centauri. This dim red dwarf lurks approximately 13,000 astronomical units from the central binary pair so far that it takes more than 5,000,000 years to complete a single orbit around the system's center of mass. Proxima is barely a star by any generous definition. It burns with less than 1% of solar luminosity. On a dark night, it would be invisible to the naked eye from Earth, despite being the single closest stellar object to our Sun at 4.24 light-years. Proxima already has confirmed planetary companions. At least 2 worlds have been detected orbiting this dim stellar ember, with a possible third candidate still under investigation. But these planets orbit a star so fundamentally different from our Sun that calling them analogues for Earth misrepresents reality. Red dwarf stars are violent flare-prone and gravitationally dominant over their close planetary companions in ways that create profoundly hostile environments for anything resembling terrestrial life. Finding planets around Alpha Centauri A or B would be something different altogether. It would mean finding worlds orbiting stars that genuinely resemble our own Sun, worlds heated by radiation with a similar spectral character to what warms Earth, worlds that might exist in conditions genuinely comparable in at least some meaningful sense to what made our planet capable of generating life. This is why astronomers have obsessed over Alpha Centauri A and B for the better part of a century. Not because proximity alone makes the system interesting, though it does, but because proximity combined with solar similarity creates a target of unique scientific and philosophical importance. Does our nearest Sun-like stellar neighbor have planets? That question carries a weight that mere astronomical curiosity cannot fully explain. It touches something deeper, something that has to do with how alone we are or are not in the part of the universe we might someday hope to reach. The history of searching for planets around Alpha Centauri is a history of disappointment. For most of the 20th century, the dominant technique for detecting exoplanets around any star was called astrometry. The principle is conceptually simple. A planet orbiting a star exerts a gravitational pull on that star, causing it to trace a tiny ellipse around the system's center of mass rather than moving in a perfectly straight line across the sky. By precisely measuring the star's position over many years, astronomers hope to detect these subtle deviations from straight-line motion and infer the presence of orbiting companions. Alpha Centauri seemed ideal for astrometric searches. Its proximity meant that any wobble would appear larger on the sky than the same wobble around a more distant star. In 1942, the Dutch-American astronomer Dirk Royal and his colleague Erich Holmberg announced the detection of a dark companion orbiting Alpha Centauri based on astrometric measurements stretching back decades. The astronomical community took notice. Our nearest neighbor appeared to host a massive planet. The announcement was wrong. Subsequent analysis revealed that the detection arose from systematic measurement errors in historical positional data, not from a genuine planetary companion. The apparent wobble was an artifact of imprecise instrumentation, not a record of gravitational interaction. Alpha Centauri's secret remained intact. Similar episodes repeated themselves over the following decades. Hopeful detections, rigorous follow-up investigations, corrections showing that the original signal arose from measurement error or observational artifact. Each disappointment refined the instruments and methods used in subsequent searches, but none produced a confirmed detection. The star that should have been the easiest exoplanet hunting target in existence repeatedly defeated every attempt to reveal what might be orbiting it. In 2012, a team using the high-accuracy radial velocity planet searcher spectrograph at the European Southern Observatory announced what briefly seemed like a genuine breakthrough. They detected a periodic Doppler shift in the light from Alpha Centauri B, consistent with a roughly Earth-mass planet in an extremely close orbit, completing one revolution every 3.2 days. The announcement generated enormous excitement in the astronomical community and considerable public attention. The detection evaporated upon closer scrutiny. Subsequent analysis by multiple independent teams revealed that the apparent signal arose from subtle variations in the way stellar noise was modeled and removed from the data. The planet had not been hiding in the radial velocity measurements. It had been created by them, a ghost produced by the interaction between imperfect noise models and the star's own intrinsic variability. Once again, Alpha Centauri had deflected inquiry with apparent effortlessness, yielding false signals that dissolved under examination. This is the scientific backdrop against which the events of August 2024 must be understood. When researchers reported detecting S1, they were not announcing a routine discovery of the type that had become almost commonplace in the exoplanet era. They were claiming success in an observational campaign that had resisted every prior attempt spanning more than 80 years. They were asserting that a telescope designed to study the most distant objects in the observable universe had detected a Saturn-mass world orbiting in the habitable zone of our nearest sun-like stellar neighbor. They were saying in effect that the longest-standing open question in solar neighborhood astronomy might finally have an answer. The extraordinary weight of that claim is why what followed the disappearance of the signal in early 2025 created such profound scientific discomfort. To understand what JWST found and why it might have found and then lost it, you first need to understand why Alpha Centauri defeated every previous attempt at planetary detection. The reasons are not arbitrary. They arise from the system's specific physical characteristics in ways that reveal something fundamental about the challenge of searching for faint objects beside blinding ones. Alpha Centauri A is the third brightest star in the Earth's night sky, surpassed only by Sirius and Canopus. Its apparent brightness arises from the combination of intrinsic luminosity and extraordinary proximity. On clear nights in the southern hemisphere, it dominates the constellation Centaurus, with a yellow-white brilliance that ancient navigators used to chart courses across unknown oceans. For telescopes equipped with sensitive detectors optimized to capture faint signals, this blazing intensity is not an asset, it is a catastrophe. Think of it this way. Imagine you are standing in a darkened room, holding a single candle, trying to examine a firefly hovering 6 inches from the candle's flame. The flame is not merely brighter than the firefly, it is so overwhelmingly brighter that its light floods your retina, washing out every detail in its vicinity. Moving the firefly further from the flame helps only so much. At some point, the light dispersed by the flame still reaches the space where the firefly hovers, drowning whatever faint signal the insect itself produces. This is roughly the observational situation astronomers face when searching for planets around Alpha Centauri A. The brightness ratio between the star and a Saturn-mass planet orbiting within its habitable zone exceeds 10,000 to 1 at visible wavelengths. In the mid-infrared, where planets emit thermal radiation and the contrast between star and planet improves somewhat, the ratio still approaches several thousand to 1. Finding the planet requires instruments capable of detecting signals thousands of times fainter than the overwhelming stellar glare surrounding them. The binary companion amplifies these difficulties in ways that have no analog in searches around single stars. Alpha Centauri B currently orbits approximately 20 astronomical units from its companion. During observations of Alpha Centauri A, the secondary star floods detectors with contaminating light that scatters across the entire field of view. No coronagraph in existence can simultaneously block two bright stars positioned at different locations on the detector. Every attempt to suppress Alpha Centauri A's glare leaves massive residual contamination from its stellar sibling blazing nearby. Additionally, Alpha Centauri A moves. It possesses one of the largest proper motions of any naked-eye star, racing across the celestial sphere at approximately 3.7 arcseconds per year. This motion sounds tiny, but it represents measurable displacement during observations requiring exquisite positional stability. A telescope trying to maintain precise pointing on Alpha Centauri A must continuously compensate for this motion while simultaneously suppressing stellar glare and tracking across a background crowded with unrelated stars because the system lies nearly in the plane of the Milky Way, where thousands of faint background objects crowd every field of view. Each of these challenges alone would complicate any observational campaign. Together they conspired to make Alpha Centauri A essentially untouchable for every previous generation of planet-hunting technology. What changed was not the star. What changed was us. The James Webb Space Telescope was not built to look at nearby stars. This sentence requires a moment to sit with because it contains a paradox that explains everything about why the Alpha Centauri observations were so audacious and so technically demanding. JWST, the most complex and expensive scientific instrument humanity has ever deployed in space, costing approximately $10 billion and requiring more than 20 years of design, construction, testing, and deployment, was optimized for a specific class of target, objects so distant that the light reaching its detectors has been traveling since the early universe, galaxies forming when the cosmos was less than 1 billion years old, the faint infrared glow of primordial stellar populations that existed before our own sun was born. The telescope's golden mirrors, its sun shield, the size of a tennis court, its orbit at Lagrange point 2, 1 million miles from Earth. All of these design choices reflect a mission focused on the very far rather than the very near. Pointing this instrument at Alpha Centauri is in a sense like using a submarine to climb a mountain. The tool is exquisitely well suited for an entirely different environment than the one you are asking it to operate in. And yet, among the astronomers who had spent careers dreaming about Alpha Centauri's planetary family, one man refused to accept that JWST's design parameters represented an uncrossable boundary. His name is Charles Beichmann, a veteran astronomer at NASA's Jet Propulsion Laboratory and the NASA Exoplanet Science Institute. Beichmann had been thinking about how to detect planets around our nearest stellar neighbor since long before the telescope that would eventually make the attempt even existed on paper. He understood the difficulties with precise clarity. He also understood something that pure technical pessimism can obscure. Difficult is not the same as impossible. The conceptual breakthrough that made the Alpha Centauri observation thinkable arrived from an unexpected direction. Instead of trying to detect planets through reflected starlight, Beichmann's approach would search for thermal emission. The physics of this distinction matters enormously. Every object with a temperature above absolute zero radiates energy. The wavelength at which that radiation peaks depends on the object's temperature. Extremely hot objects like stellar surfaces, burning at thousands of degrees, emit most powerfully at visible and ultraviolet wavelengths. Cooler objects emit at longer wavelengths, shifting progressively into the infrared as temperature decreases. A planet orbiting in the habitable zone of a sun-like star sits at a temperature somewhere between roughly 200 and 350 Kelvin. That range corresponds to thermal emission peaking at mid-infrared wavelengths around 15 micrometers, a spectral region where the contrast between a star and its planetary companion improves dramatically compared to visible light. Alpha Centauri A has existed for approximately 5 billion years, roughly the same age as our Sun. Any planets orbiting this mature star would have lost the formation heat that makes young planets relatively easy to image. They would be cold by astronomical standards, cool enough that their thermal emission falls precisely in the mid-infrared range where JWST's mid-infrared instrument, known by its acronym MIRI, achieves peak sensitivity. The instrument contains a specialized component called a 4-quadrant phase mask coronagraph. This device works through a principle that seems almost magical until you understand the underlying physics. The coronagraph places a carefully engineered optical mask over the position of the star on the detector. This mask exploits the wave nature of light, creating conditions where light waves from the blocked star arrive at the detector in configurations that cancel each other out through destructive interference. The waves combine in ways that cause them to subtract from each other rather than add together, reducing the star's brightness by factors of hundreds or thousands, while leaving light arriving from slightly different directions, including from a nearby planet relatively unaffected. The result is an artificial eclipse. The star's overwhelming glare is suppressed. Whatever orbits beside it becomes visible in the comparative darkness the coronagraph creates. For most stellar targets, this arrangement functions beautifully. Stars at typical exoplanet hunting distances present manageable brightness levels. Standard operational procedures work smoothly, but Alpha Centauri A presented complications that standard procedures were entirely unprepared to handle. The first problem was the star's brightness. JWST's target acquisition system, the set of procedures by which the telescope locks onto a star and positions it precisely behind the coronagraph mask, was designed with specific brightness limits in mind. Those limits existed for good reason. Pointing extremely sensitive detectors at overwhelmingly bright sources risks causing permanent damage. The fine guidance sensors that maintain pointing accuracy were not engineered to handle the intensity Alpha Centauri A would deliver if observed directly. Standard acquisition procedures would fail, and they might fail in ways that damaged hardware that could never be repaired at a distance of 1 million miles from Earth. The second problem was the binary companion. Alpha Centauri B orbits close enough to its partner that during current epochs, its brilliant light floods MIRI's detector when the telescope points toward the system. No coronagraph can simultaneously suppress two stars at different positions. Blocking Alpha Centauri A perfectly still leaves the companion's light scattering across the field in ways that contaminate every region where a planetary signal might appear. The third problem was motion. Alpha Centauri's rapid proper motion across the sky means the star's position at any given moment differs measurably from its position calculated using older astrometric data. The coronagraph requires the target star to be positioned behind the mask center with an accuracy of better than 10 milliarcseconds. Errors even slightly larger than this threshold degrade coronagraphic performance and allow stellar light to leak around the mask edges. Precisely positioning a rapidly moving star behind a small mask without ever directly pointing the sensitive telescope at that star required a level of astrometric precision that no previous JWST observation had demanded. The fourth problem was the galactic background. The Alpha Centauri system lies almost directly in the plane of the Milky Way. This means that every image taken toward the system contains thousands of unrelated background, stars, galaxies, and other astronomical sources. Any potential planetary detection must be carefully distinguished from this crowded cosmic backdrop. A faint point of light, appearing beside Alpha Centauri, A might be a planet orbiting 4 light-years away, or might be a distant galaxy, billions of light-years beyond, perfectly aligned by cosmic coincidence. Beichmann's team addressed each of these obstacles through a combination of innovative engineering and methodical preparation that took months to develop and refine. The solution to the brightness problem emerged from a technique called blind offsetting. Rather than pointing JWST directly at Alpha Centauri A, which would trigger brightness limits and risk detector damage, the team identified a nearby reference star with manageable intensity. They selected Epsilon Muscae, a red giant approximately 330 light-years from Earth in the constellation Musca. This distant stellar furnace provides brightness levels that fall comfortably within JWST's standard operational parameters. The telescope's guidance systems could lock onto Epsilon Muscae without difficulty. From this reference position, with the telescope's pointing system locked and stable, the team would then command a precisely calculated blind maneuver. The telescope would slew by a specific angular distance in a specific direction, moving from Epsilon Muscae to a position that placed Alpha Centauri A behind the coronagraphic mask, all without ever directly acquiring the brilliant target. The star would arrive at the correct position through calculated offset rather than through direct observation. The precision required for this maneuver is difficult to convey in ordinary terms. The offset distance and direction needed to be known with an accuracy of a few milliarc seconds. For reference, 1 milliarc second is approximately the angle subtended by a human hair viewed from a distance of roughly 2 miles. The team needed to know Alpha Centauri A's exact position at the precise moment of each observation, accounting for the star's rapid, proper motion across the sky. Its significant parallax shift as Earth moved through different positions in its annual orbit around the Sun, and the geometric relationship between Epsilon Muscae and Alpha Centauri A, as seen from JWST's position at Lagrange Point, R. Parallax is particularly consequential at Alpha Centauri's distance. Because the star is so close to Earth, our planet's orbital motion causes the star to appear to shift back and forth against the distant background by approximately 750 milliarc seconds over the course of each year. This is an enormous motion by the standards of stellar astrometry. Coordinates valid for an observation in January would place the star at the wrong position behind the coronagraph if used without modification in March. Every individual observation required freshly computed offset coordinates incorporating the precise date and time of execution. The team developed software pipelines capable of automatically calculating updated values based on observation scheduling. They incorporated data from the Gaia spacecraft, which had precisely measured Alpha Centauri's position, proper motion, and parallax to accuracies surpassing any previous measurements. They simulated the blind offset procedure thousands of times using these parameters, testing whether the calculated positions would correctly place the star behind the coronagraph center under realistic observational conditions. Addressing the binary companion problem required a different kind of solution, one based not on preventing contamination but on removing it after the fact. Alpha Centauri B could not be blocked by the coronagraph. Its scattered light would inevitably appear in every image. The team developed specialized data reduction techniques designed to characterize this contamination pattern precisely and subtract it from the science data without simultaneously removing genuine planetary signals that might be hiding beneath it. These algorithms required reference observations of stars with similar brightness and color to Alpha Centauri B observed through identical coronagraphic configurations to provide templates of what the companion's scattered light contribution looks like in processed images. By comparing these templates against Alpha Centauri observations and removing correlated patterns, the data reduction pipeline could strip away the companion's influence while preserving residual astronomical signals associated only with the primary target. The galactic background problem demanded a different strategy entirely. Because the field around Alpha Centauri is crowded with unrelated objects, any candidate detection must be tested against archival imaging from multiple previous observatories, spanning decades of observations. A genuine planetary companion orbits its host star, and should appear to move along with the rapidly moving Alpha Centauri system against the background. A background galaxy, or unrelated star, would remain stationary while Alpha Centauri swept across the sky at its characteristic velocity. Crucially, the team also incorporated information from a 2019 observation that had been mostly set aside in the years since it was obtained. Astronomers using the Very Large Telescope in Chile's Atacama Desert, operating an instrument called NACO, specifically designed for high-contrast mid-infrared imaging, had detected a marginal signal near Alpha Centauri A, designated Sentinel. This ground-based detection appeared at approximately 1.1 astronomical units from the star, slightly closer in than the JWST S1 detection would later appear. The signal never achieved sufficient statistical robustness to be claimed as a confirmed detection. Earth's atmosphere introduces distortions and noise sources that ground-based coronagraphy cannot fully eliminate, even with adaptive optics systems designed to correct atmospheric seeing in real time. The C1 signal was filed away as an intriguing hint requiring better data rather than a genuine planetary detection. But the possibility that C1 and S1 might represent the same object viewed at different orbital phases would become critically important when the time came to interpret what the 2025 follow-up observations failed to fin. The first actual observation attempts with JWST came in 2023. They failed completely. Technical difficulties rendered the data entirely unusable. The blind offset procedure placed the star at incorrect positions. Coronagraphic performance degraded far below levels required for useful planet searches. The binary companion scattered light dominated the field in ways the data reduction pipeline could not adequately address. The telescope that had so effortlessly revolutionized our understanding of the distant universe struggled profoundly with an object 4 light-years away. Failure would have discouraged many teams. The difficulties appeared to confirm what skeptics had predicted from the proposal stage. Alpha Centauri was simply too challenging for JWST. The telescope should return to its designed mission rather than attempt impossible observations of nearby bright stars. Beichmann's team did not return to a different mission. They spent months analyzing every aspect of the 2023 failure. They identified the specific sources of positional error in the blind offset procedure and recalculated the astrometric inputs using more precise Gaia measurements with additional corrections for systematic biases in the stellar position data. They redesigned the data reduction pipeline to better characterize and subtract the binary companion's contribution. They developed new pointing stability tests to verify that the telescope maintained adequate precision throughout extended observation sequences. In mid-2024, they implemented this refined approach through a series of test observations that confirmed the modifications worked. JWST could now observe Alpha Centauri A with sensitivity approaching theoretical limits, a performance level that had seemed unreachable during the 2023 failures. The operations team at the Space Telescope Science Institute granted the go-ahead for full science observations. In August of 2024, the James Webb Space Telescope executed 3 long observation sequences pointed at Alpha Centauri A. Each exposure lasted hours. The coronagraph suppressed stellar glare. The detectors collected whatever faint signals emerged from the surrounding space. The blind offset maneuver placed Alpha Centauri A behind the mask with the precision that months of refinement had made possible. Alpha Centauri B blazed in the upper portion of each frame, its contamination spreading across the field in patterns the reduction pipeline had been trained to recognize and remove. The raw images that streamed back to Earth from Lagrange Point 2 looked to untrained eyes like abstract noise. Chaotic combinations of diffraction patterns, scattered light detector artifacts, and statistical fluctuations covered every frame. No human being could identify any meaningful astronomical signal by looking directly at what the telescope had captured. The data required processing. What processing revealed would change the course of Alpha Centauri research forever. The team employed a method called reference star differential imaging. Multiple other stars had been observed through identical coronagraphic configurations specifically to create templates showing how the instrument behaves in the absence of a planetary companion. These reference observations captured the systematic patterns arising from JWST's optics, the coronagraph's diffraction structure, and the specific detector response under these unusual observing conditions. Subtracting these templates from the Alpha Centauri data removed systematic contamination while preserving any genuine astronomical signals unique to the target system. Additional algorithms based on principal component analysis identified and removed correlated noise patterns that simple template subtraction left behind. These mathematical techniques decompose the data into independent components, isolating and stripping away contributions from systematic effects, while preserving the residual signal structure that cannot be explained by known instrumental behavior. Layer by layer, the processing stripped contamination away. And there, at a separation of approximately 1.5 arcseconds from Alpha Centauri A, a faint point of light emerged from the noise. It shone more than 10,000 times fainter than its host star. Its position placed it roughly 2 astronomical units from Alpha Centauri A. Its brightness at 15.5 micrometers wavelength corresponded to thermal emission from an object with an effective temperature of approximately 225 Kelvin, frigid by terrestrial standards, but consistent with a world absorbing and re-radiating warmth from the nearby stellar furnace. The detection achieved 5.5 sigma statistical significance. In experimental science, a 5 sigma threshold is generally considered sufficient to claim a discovery. The probability of random noise producing a signal this strong by chance falls below 1 in 3.5 million. At 5.5 sigma, that probability drops still further. Rigorous statistical tests designed to identify false positives, tests involving independent analysis of separate data subsets, injection and recovery experiments, inserting simulated planetary signals into raw data, cross-referencing against every available catalog of background astronomical sources, all returned the same conclusion. Something real had been detected beside our nearest sun-like stellar neighbor. The astronomical community braced itself for what confirmation might mean. Before we follow S1 into its disappearance, we must first understand what it appeared to be. A detection at 5.5 sigma is not merely a data point. It is a portrait incomplete and blurred at its edges, but a portrait nonetheless. The brightness of the signal, the wavelength at which it was detected, the angular separation from the host star, all of these measurements encode physical information about whatever produced them. Astronomers know how to read this information the way a physician reads an X-ray, not with perfect certainty, but with enough precision to say meaningful things about what lies beneath the surface. Begin with temperature. The thermal emission detected at 15.5 micrometers wavelength, combined with the object's brightness, yields an effective temperature of approximately 225 Kelvin. Convert that to more familiar terms, and you arrive at roughly -48 degrees Celsius. This is cold by any terrestrial standard. Water freezes solid at this temperature. Carbon dioxide liquefies. The air you breathe would condense into a faint frost on any surface exposed to such conditions. And yet, in the context of the outer solar system, 225 Kelvin is relatively warm. Saturn, orbiting our Sun at an average distance of roughly 9.5 astronomical units, maintains cloud-top temperatures around 134 Kelvin. Neptune, at 30 astronomical units, plunges to approximately 55 Kelvin. The comparative warmth of S1 reflects its position within Alpha Centauri A's habitable zone, that circumstellar region where temperatures permit the existence of liquid water on suitably configured surfaces. Alpha Centauri A pumps out roughly 50% more energy than our Sun and S1 orbits, at distances between approximately 1 and 2 astronomical units, receiving a flux of stellar radiation that keeps its outer atmosphere considerably warmer than the icy giant worlds of our own outer solar system. The temperature also tells us something important about what S1 is not. Newly formed planets glow brightly from the heat of their formation, the energy released during the violent process of gravitational collapse that assembled them from dispersed dust and gas. A young Jupiter-mass world radiating formation heat would appear dramatically brighter in JWST's detectors than S1 appears. Alpha Centauri A is approximately 5 billion years old. Any planets orbiting it have had 5 billion years to radiate away their formation energy. S1's modest thermal emission is exactly what you would expect from a mature world that has long since lost its primordial glow, surviving now only on the warmth it absorbs from its host star and whatever residual internal heat, gravitational compression, and radioactive decay continue to supply. This maturity matters enormously. Every other planet that has ever been directly imaged orbits a young star, typically less than 100 million years old. These juvenile worlds blaze with formation heat that makes them relatively easy to detect despite their great distances from Earth. They represent planetary systems in their infancy, still assembling, still settling. Nothing like the ancient stable configurations we observe in our own solar neighborhood. S1, if confirmed, would be the oldest directly imaged exoplanet by an enormous margin. It would offer the first direct view of a mature gas giant, as it actually exists after billions of years of evolution, cooled, settled, ancient, in the way that Earth and Jupiter and Saturn are ancient. Now, consider mass. Translating observed brightness and temperature into a planetary mass requires models of how gas giant atmospheres emit thermal radiation at different masses and ages. These models carry uncertainties, but they consistently place S1 in the Saturn-class range rather than the Jupiter-class range. Saturn contains approximately 95 Earth masses. Jupiter dominates at 318 Earth masses. The distinction between these categories is not merely quantitative. Saturn and Jupiter possess genuinely different internal structures, different atmospheric chemistry, different evolutionary histories. A Saturn-mass world is a substantially less imposing object than a Jupiter-mass one, though it remains a gas giant utterly unlike anything terrestrial. The radius estimates for S1 fall between approximately 1 and 1.1 Jupiter radii. This means the planet's physical size roughly matches Jupiter's enormous bulk, despite containing less than half the mass. The combination of modest mass and substantial radius implies a very low bulk density, lower than liquid water. If you could somehow place S1 in an ocean large enough to contain it, it would float. This low density confirms a composition dominated by hydrogen and helium, the lightest elements in the periodic table, accumulated from the primordial nebula gas during the earliest stages of planetary formation. Gas giants form quickly. This is not metaphorical. It is a physical necessity imposed by the timescales of stellar system evolution. The hydrogen and helium that eventually becomes a gas giant's atmosphere exists initially as nebula gas surrounding a newly formed star. This gas is not bound to any particular location. It is subject to radiation pressure from the growing star dispersal by stellar winds and heating that prevents it from cooling and condensing into solid material. Computer models consistently find that the window during which nebula gas remains available for planetary accretion lasts only a few million years before the developing star's output drives the gas away. A planet that will become a gas giant must accumulate a rocky or icy core of roughly 10 Earth masses within this brief window. Once the core reaches this critical threshold, its gravity becomes strong enough to capture and retain the surrounding gas in vast quantities. The process accelerates rapidly. A 10 Earth mass core can grow to Saturn's mass in less than 1 million years if sufficient gas remains available. Then the window closes. The star's radiation clears the remaining nebula, and any planetary cores that have not yet reached the critical accretion threshold remain forever as ice giants or rocky super-Earths, never accumulating the massive atmospheres that define true gas giants. S1's existence, therefore, tells us something about the early evolution of the Alpha Centauri system. A massive rocky core formed quickly enough within the nebula's brief lifetime to trigger runaway gas accretion. The binary companion's gravitational influence did not prevent this process from completing. Whatever disruption Alpha Centauri B imposed on the primordial disk around Alpha Centauri A, it was not sufficient to prevent at least one gas giant from assembling itself within the first few million years of the system's existence. Now consider where S1 orbits. The orbit presents some of the most scientifically fascinating and theoretically challenging aspects of this entire detection. Based on the two positive detections available at the time of the discovery papers, the August 2024 JWST observation placing S1 at approximately 2 astronomical units from Alpha Centauri A, and the 2019 Very Large Telescope detection placing the C1 candidate at approximate 1.1 astronomical units. The orbital analysis paints a picture of a world following a significantly eccentric path. Orbital eccentricity is a measure of how far an orbit deviates from a perfect circle. A circular orbit has eccentricity 0. A parabolic escape trajectory has eccentricity 1. Everything between those values describes an ellipse with higher values, indicating more elongated, more extreme ellipses. Earth's orbit has an eccentricity of roughly 0.017, nearly circular. Mars reaches 0.093. Mercury, the most eccentric major planet in our solar system, achieves 0.206. S1's estimated eccentricity centers around 0.4. This means the planet's distance from Alpha Centauri A varies dramatically throughout each orbital cycle. At its closest approach, called perihelion S, one passes within roughly 1 astronomical unit of its host star, approximately the same distance Earth maintains from our Sun. At its most distant point, called aphelion, it retreats to nearly 2 astronomical units, approaching the orbital radius of Mars in our own solar system. This wide swing through varying stellar distances creates enormous changes in the amount of radiation the planet receives across a single year. Near perihelion S, one receives roughly 4 times as much stellar energy as it does near aphelion. These dramatic seasonal variations drive atmospheric dynamics in ways we can currently only model through computer simulations calibrated against what we observe in Jupiter and Saturn. Cloud formation patterns would shift dramatically. Chemical equilibrium states governing which molecules exist in which atmospheric layers would change. Storm systems might intensify and weaken in rhythms tied to the planet's eccentric passage through regions of varying stellar flux. The orbital period remains uncertain given available data, but falls somewhere between 2 and 3 Earth years based on current constraints. More puzzling than the eccentricity is the inclination. Alpha Centauri A and B orbit each other along a well-determined path inclined approximately 79 degrees from our line of sight. Planets forming from material in the primordial disk around Alpha Centauri A should generally inherit that disk's orientation, which itself reflects the angular momentum of the material from which the system formed. Standard planetary formation models predict that planets should orbit in roughly the same plane as the binary system, simply because both the binary orbit and the planetary disk trace back to the same rotating cloud of gas and dust that collapsed to form the entire stellar family. S1 appears to orbit at roughly 50 degrees inclination relative to the binary orbital plane. This misalignment of approximately 30 degrees is not a measurement error. It is a genuine physical characteristic of the orbit that demands explanation. Several mechanisms could produce it. Perhaps S1 formed in a normally aligned orbit and was subsequently tilted through gravitational interactions with other planets that have since been ejected from the system. Perhaps the primordial disk itself was warped by gravitational torques from the binary companion before planets finished forming, imprinting a tilted geometry on the planetary orbits from the beginning. Perhaps S1 experienced a close encounter with a massive body during the system's early chaotic period that permanently altered its orbital plane. Each of these possibilities generates testable predictions. If other planets exist in the system, their orbital inclinations might reveal something about how the architecture became misaligned. If the binary orbital plane itself shows subtle signatures of past dynamical upheaval, those signatures might connect to S1's unusual configuration. Future observations with sufficient precision to measure orbital evolution over decades would detect the slow precession of S1's orbit as the binary companion's gravity gradually torques it, providing information about the comstotal dynamical history that shaped the current configuration. But all of this analysis, the temperature, the mass, the eccentric and inclined orbit, became secondary in the months following the August 2024 discovery. Because in February and April of 2025, something happened that transformed a remarkable detection into a profound scientific puzzle. S1 disappeared. The February 2025 observation proceeded without technical difficulties. The blind offset placed Alpha Centauri A precisely behind the coronagraph mask. MIRI collected photons for hours. The data reduction pipeline processed the incoming information using procedures identical to those that had revealed S1 6 months earlier. Reference star subtraction stripped away systematic contamination. Principal component analysis removed correlated noise. Layer after layer of instrumental signature was peeled away, leaving behind whatever genuine astronomical signal the system contained. Nothing appeared at S1's expected position. Not a marginal detection requiring careful interpretation, not a weak signal hovering near statistical threshold, simply nothing. The region where S1 had blazed with 5.5 sigma significance showed only the random fluctuations expected from an empty field. The planet had not faded. It had not dimmed to a lower brightness level requiring longer integration to detect. It had, in the language of the astronomers who searched for it, vanished. Anaga Sangangi, a doctoral student at the California Institute of Technology and co-first author on the discovery papers, described the situation with a phrase that captured the scientific community's bewilderment precisely. They faced, she said, the case of a disappearing planet. The April 2025 observations produced identical results: empty fields, null detections, no trace of the object that had generated so much excitement during the summer of the previous year. This outcome demanded explanation. Planets do not simply vanish. Objects bound gravitationally to a star follow predictable, elliptical paths governed by the same physics that Newton codified in the 17th century and Einstein refined in the 20th. If S1 genuinely orbited Alpha Centauri A, it should appear somewhere in every observation, even if its position changed according to orbital motion. The fact that it appeared nowhere at all in 2 successive observation campaigns was deeply unsettling. 3 explanations emerged, each with distinct implications for understanding what JWST had actually detected. The first and most deflating possibility was that S1 had never been real. Despite surviving every statistical test and artifact rejection criterion the team could devise, despite achieving 5.5 sigma significance that placed false positive probability below 1 in 10 million, despite producing consistent signals across independent subsets of the August data, the detection might represent an extraordinarily improbable fluctuation in detector noise. Random processes occasionally produce patterns that appear significant. Electronic detectors experience quantum fluctuations. Cosmic rays strike individual pixels. Complex systematic effects interact in unpredictable ways. Any of these phenomena might, in rare circumstances, conspire to mimic a genuine astronomical detection with convincing statistical characteristics. This explanation feels deeply unsatisfying to scientists who understand what 5.5 sigma actually means. The threshold of 5 sigma exists precisely because it excludes false positives at the level of less than 1 in a million. Claiming that a false positive nonetheless occurred requires accepting extraordinary statistical misfortune. Furthermore, the team had specifically tested the detection by splitting the August observations into independent halves and analyzing each separately. Both halves reproduced S1 at consistent positions and brightnesses, a behavior that genuine noise fluctuations rarely exhibit across independent data samples. And yet, statistics never reduce false positive probability to 0. The universe contains enough observations that even extraordinarily rare coincidences must occasionally happen somewhere. Perhaps Alpha Centauri became the site of precisely that misfortune. The second possibility involved contamination from an unknown background source. Every image of Alpha Centauri captures not just the nearby stellar system, but everything along the line of sight through the galaxy. A compact, distant galaxy, or an extremely faint, uncharted background star might have occupied the S1 detection position during August observations, producing a signal subsequently attributed to a planetary companion. If this background object possessed significant proper motion of its own, or had simply drifted slightly due to its own orbital characteristics, it might have vacated the detection position by February, creating both the initial signal, the subsequent non-detections. The team investigated this possibility with exhaustive thoroughness. They cross-referenced the S1 detection position against every available astronomical catalogue. They searched Gaia's measurements of nearly 2 billion stellar positions and found no known source near the detected location. They examined archival images from multiple ground-based and space-based telescopes spanning decades and found no background object at the relevant position with sufficient brightness to account for the August signal. They analyzed the spectral characteristics of the detected emission and found them consistent with a cool planetary atmosphere rather than a background galaxy. Every test designed to expose background contamination came back negative. The third possibility was the one that transformed the disappearance from a failure of the planetary hypothesis into evidence consistent with it. S1 might be a completely genuine planet that had moved beyond the coronagraph's detection sensitivity between observation epochs through entirely ordinary orbital mechanics. Understanding why this explanation works requires confronting something counterintuitive about coronagraphic imaging. These instruments do not provide uniform detection capability at all positions around a blocked star. The 4-quadrant phase mask coronagraph used by MIRI creates an artificial eclipse by exploiting destructive interference, but diffraction, the tendency of light waves to bend around edges, fundamentally limits how completely any physical mask can suppress stellar radiation. Light bends around the mask boundaries, creating complex patterns of residual brightness that extend outward from the stellar position. Close to the star, this diffracted light overwhelms any planetary signals. Too far from the star, the planet's signal becomes too faint to detect against detector noise. Between these limits lies a detection sweet spot, a range of angular separations where sensitivity is sufficient to find planets, but this sweet spot is narrower than it might appear and varies dramatically with position angle around the blocked star. The 4-quadrant mask's geometry interacts with JWST's optical structures to create regions where coronagraphic suppression works excellently and adjacent regions where residual contamination remains prohibitively high. A planet positioned at a favorable angle from its star might be clearly detectable in August and completely invisible in February if its orbital motion carried it to an unfavorable angular position where the coronagraph fails to suppress stellar light adequately. Additionally, S1's eccentric orbit means its distance from Alpha Centauri A changes continuously. Near perihelion, the planet approaches close enough to the star that it enters regions where diffracted stellar light dominates the field, rendering it invisible regardless of coronagraphic performance. Only near aphelion, when the planet reaches its maximum separation from the star, does it emerge into the region where MIRI achieves sufficient contrast for detection. The August 2024 observation apparently captured S1 near aphelion, positioned at approximately 2 astronomical units, where the coronagraph could marginally detect its thermal emission. By February and April of 2025, the planet's eccentric orbit had carried it toward perihelion, shrinking its angular separation from the star and drawing it into the zone of coronagraphic blindness. The planet had not vanished. It had simply moved somewhere that current technology could not follow. To test whether this orbital explanation could genuinely account for the disappearance, the research team conducted an extensive computational analysis. They generated millions of simulated planetary orbits spanning the full range of parameters consistent with the available detections and non-detections. Each simulated orbit had to simultaneously place the planet at approximately 1.1 astronomical units during the 2019 ground-based observation, at approximately 2 astronomical units during the August 2024 JWST detection, and in regions beyond coronagraphic sensitivity during both the February and April 2025 follow-up campaigns. Each orbit also had to remain gravitationally stable over billions of years in the presence of Alpha Centauri B's gravitational influence. The computational results were striking. 52% of all gravitationally stable orbits fitting the combined astrometric positions produced natural non-detections in both February and April 2025. More than half of the allowed orbital configurations would cause the planet to disappear from JWST's coronagraphic field during exactly the months when scientists searched for it. The non-detections were not anomalies requiring special explanation. They were the statistically expected outcome for a majority of the orbital solutions consistent with the data. This single calculation transformed the scientific interpretation of the 2025 follow-up observations entirely. Rather than contradicting the planetary hypothesis, the non-detections remained fully consistent with S1's existence across the majority of allowed orbital configurations. A real planet following any of these paths would appear in August 2024 to vanish in early 2025, and return to detectable positions at some predictable future date when its orbit carried it back through the coronagraph sensitivity zone. The absence of detection was not evidence against the planet. It was evidence of an orbital geometry that science had not yet constrained precisely enough to know in advance where the planet would be. But this conclusion carried an important caveat. The orbital solutions consistent with all available data spanned an enormous range of possible configurations. Eccentricities between roughly 0.2 and 0.6, periods between 18 months and 4 Earth years, inclinations from 30 to 70 degrees. Each combination predicted different future visibility windows, different orbital speeds, different positions at any given future date. The computational analysis could identify that S1's existence remained consistent with the non-detections, but it could not yet specify precisely when the planet would return or exactly where it would appear when it did. What the models could say was this: based on the family of stable orbits consistent with all available observations, the planet should approach aphelion again, sometime in mid-2026. The August 2026 observation window represented the most probable period for redetection based on statistical analysis of the allowed orbital configurations. If JWST observed Alpha Centauri A during this window and found S1 near its predicted position, the case for planetary confirmation would become overwhelming. A third independent detection tracked across an orbital arc, spanning 7 years of observations, including the 2019 ground-based hint, would demonstrate gravitationally bound motion with a clarity that no statistical fluctuation or background contamination could mimic. The research team documented their findings in 2 peer-reviewed papers accepted by the Astrophysical Journal Letters. The first paper presented the observational details, the detection characteristics, the photometric measurements, and the orbital analysis. The second paper described the sophisticated image processing methodology and the systematic error analysis required to extract marginal signals from data collected under such extreme observational conditions. Both papers were careful to describe S1 as a candidate planet rather than a confirmed detection, because that careful language reflects the actual state of the evidence. One robust detection, however, statistically compelling, cannot definitively prove planetary nature without the corroboration of tracked orbital motion across multiple epochs. The scientific community received the papers with the mixture of cautious skepticism and barely suppressed excitement that genuinely significant results tend to produce. Skeptics pointed to the single detection epoch. They noted that extraordinary claims required extraordinary evidence, and that one observation, however, clean could not substitute for tracked orbital motion. They asked whether the 2019 ground-based detection truly represented the same object, or might be a coincidental alignment of noise features from a completely different observational epoch and instrument. Those who found the results compelling pointed to the statistical strength of the August detection, to the exhaustive artifact rejection testing, to the consistency between C1 and S1 as potential observations of the same object, different orbital phases, and most powerfully to the fact that the disappearance itself was the expected outcome for more than half the allowed orbital configurations. The planet's absence in 2025 was not a problem for the planetary hypothesis. It was a feature of it. The universe, as it so often does, declined to make things easy. Set aside for a moment the question of whether S1 is real. Set aside the statistics, the orbital models, the competing hypotheses about background contamination and noise fluctuations. Set aside the February non-detection and the April non-detection and the computational analysis showing that disappearance was the expected outcome for more than half the allowed configurations. Set aside all of it and ask instead a different question. If S1 is real, what does its existence actually mean? The answer to that question is why astronomers lose sleep over Alpha Centauri. Begin with location. S1 orbits Alpha Centauri A at distances ranging between approximately 1 and 2 astronomical units across each eccentric year. Alpha Centauri A's habitable zone, the circumstellar region where a rocky planet with a suitable atmosphere could maintain liquid water on its surface, extends from roughly 1.2 to 2.5 astronomical units, given the star's luminosity of approximately 1.5 times solar output. S1 spends the majority of its eccentric orbit within or near this zone. Near perihelion, it dips slightly inside the inner habitable boundary. Near aphelion, it retreats toward the outer edge. For most of each orbital period, this world moves through the temperature range, where water neither boils away nor freezes permanently solid. This fact alone would make S1 scientifically extraordinary if confirmed. Every other directly imaged planet orbits either far outside its star's habitable zone in the frozen outer reaches, where formation models predict giant planets typically reside, or it orbits a young hot star whose habitable zone bears no resemblance to the temperate conditions around sunlike. Stars, the directly imaged planets currently in our catalogues, are mostly young, hot, massive objects, juvenile worlds still glowing from formation heat, orbiting at tens or hundreds of astronomical units from their host stars. They tell us about planetary formation, not about the kinds of mature temperate systems that interest astrobiologists. S1 would be the first directly imaged planet occupying anything resembling a habitable zone around a sun-like star. But S1 is not a rocky world where oceans could pool and life could walk or swim or crawl across a solid surface. It is a gas giant. Its crushing atmospheric pressures, its lack of any solid surface, its hydrogen and helium-dominated composition, these characteristics make S1 itself definitively uninhabitable by any biological standard we understand. No organism that we know of, no matter how extreme its adaptations, could survive the conditions within a Saturn-mass gas giant's atmosphere. The chemistry is wrong, the pressures are wrong, the absence of solid substrate removes the foundation that terrestrial biology requires. And yet gas giants are almost never alone. This is perhaps the most important fact about gas giants that casual discussions of planetary habitability consistently overlook. Every gas giant in our solar system possesses not one planetary companion but dozens, sometimes hundreds of natural satellites, ranging from captured asteroids barely kilometers across to world-sized bodies with complex geology, thick atmospheres and subsurface oceans containing more liquid water than exists in all of Earth's oceans combined. Jupiter alone hosts more than 90 confirmed moons, the 4 largest discovered by Galileo in 1610, with one of the earliest telescopes ever turned skyward, are worlds unto themselves. Io blazes with volcanic activity more intense than anywhere else in the solar system, its surface continuously reshaped by tidal heating from Jupiter's enormous gravitational influence. Europa conceals beneath its icy crust a global ocean of liquid water, estimated at roughly 100 kilometers depth, kept liquid not by stellar warmth, but by the same tidal forces that keep Io volcanically alive. The ice shell above Europa's ocean may be only a few kilometers thick, in places thin enough that hydrothermal chemistry at the ocean floor could conceivably generate the energy gradients that microbial ecosystems exploit near deep-sea vents on Earth. Ganymede exceeds the planet Mercury in diameter and possesses its own magnetic field, the only moon in the solar system known to generate one. Callisto, the outermost large Jovian moon, likely contains a subsurface liquid water layer sandwiched between layers of ice and rock. Saturn's moon system rivals Jupiter's in scientific fascination. Titan, the largest Saturnian satellite, exceeds Mercury in size and maintains a dense nitrogen atmosphere substantially thicker than Earth's own. Complex organic chemistry pervades this atmosphere, as solar ultraviolet radiation drives reactions producing progressively larger hydrocarbon molecules that rain down onto Titan's surface. Lakes and seas of liquid methane and ethane cover portions of the landscape, fed by rivers that carve channels through water ice bedrock over geological time. The chemistry occurring on Titan today may resemble chemistry occurring on early Earth before life emerged, offering a natural laboratory for studying prebiotic organic processes under alien conditions. Then there is Enceladus, a moon smaller than the British Isles, so modestly sized that it was barely noticed among Saturn's retinue until the Cassini spacecraft arrived in the Saturn system in 2004 and discovered something that stunned planetary scientists. Geysers erupting from fractures near Enceladus's south pole spray water vapor, ice crystals and organic molecules into space in continuous plumes that feed one of Saturn's outer rings. Beneath the frozen surface lies a global subsurface ocean of liquid water, kept warm by tidal heating from Saturn's gravitational squeeze. Measurements by Cassini detected molecular hydrogen in the plumes, a signature consistent with hydrothermal chemical reactions between hot rock and liquid water at the ocean floor. On Earth, hydrothermal vents in the deep ocean support entire ecosystems of organisms that derive energy from chemical reactions rather than sunlight. Enceladus may host similar chemistry in its hidden ocean, making it one of the most compelling targets in the search for extraterrestrial life anywhere in the solar system. Now carry this knowledge across 4.37 light-years. If S1 orbits Alpha Centauri A, with a mass and size comparable to Saturn planetary formation, models strongly predict that it hosts an extensive satellite system. Moons form naturally around gas giants during the same disk-mediated process that forms the planets themselves. As a gas giant accumulates mass from the surrounding nebula material that cannot fall directly onto the planet, forms a circumplanetary disk, a miniature version of the protoplanetary disk orbiting the parent star. Within this circumplanetary disk, smaller bodies coalesce through the same processes of collision accretion and gravitational focusing that produce terrestrial planets around stars. The result is a satellite system whose architecture mirrors in miniature the planetary system surrounding the host star. Saturn's moon system formed from exactly this process. Titan, Enceladus, Rhea, Dione, Tethys, the entire retinue of Saturnian satellites assembled within a circumplanetary disk that surrounded the young Saturn as it gathered its massive atmosphere. There is no physical reason why a Saturn-mass world orbiting Alpha Centauri A should not have generated a similar system during its formation 5 billion years ago. But here is where the Alpha Centauri case becomes genuinely extraordinary. Saturn's moons are frozen. The temperature in the outer solar system, where Saturn orbits at 9.5 astronomical units from our Sun, drops low enough that water exists only as ice on moon surfaces. The liquid water beneath Enceladus's crust and within Europa's ocean exists only because of tidal heating, an internal energy source independent of solar radiation. Without tidal heating, these moons would be frozen solid from surface to core. S1 orbits within the habitable zone of Alpha Centauri A. A moon orbiting S1 would receive stellar radiation roughly comparable to what Earth receives from the Sun, perhaps somewhat more near perihelion, somewhat less near aphelion, but within the range where liquid water is thermodynamically possible en surface. Unlike the frozen moons of our outer solar system that must rely entirely on internal tidal heat to maintain subsurface oceans, a moon around S1 could potentially maintain liquid water on its surface, warmed directly by the nearby star. The way Earth is warmed. Imagine a moon the size of Titan orbiting S1 but receiving sun-like radiation rather than the dim, distant warmth that reaches Saturn. Surface temperatures on such a world could rise above water's freezing point. Rivers might flow across a landscape of water ice bedrock and silicate rock. Precipitation cycles might deliver rainfall or snowfall across different latitudinal bands. An atmosphere containing nitrogen, carbon dioxide, and water vapor might generate a greenhouse effect that further elevates surface temperatures into the range where biology as we understand it could operate. Imagine a moon with Europa-like internal structure, orbiting S1. Its subsurface ocean kept liquid by both tidal heating from the nearby gas giant and stellar radiation penetrating through an ice shell might maintain temperatures far more hospitable than the frigid conditions beneath Europa's crust. Chemical complexity in such an ocean could be orders of magnitude richer than in our solar system's ice-covered ocean worlds, given both the greater energy input from the star and the tidal chemical cycling that interior-exterior connections enable. These are not idle speculations. They follow directly from what we know about moon formation around gas giants and about the physical conditions that liquid water requires. The possibility of habitable moons around a Saturn-mass planet in the habitable zone of our nearest sun-like stellar neighbor is not science fiction. It is a straightforward application of planetary science to the specific physical parameters S1 appears to possess. We cannot observe these hypothetical moons. The angular separation between S1 and any satellite it might host would be completely unresolvable from Earth's distance with any existing or near-future technology. A moon orbiting S1 at a distance comparable to Titan's orbit around Saturn would subtend an angle of roughly 10 micro-arcseconds, as seen from Earth, approximately 1/10,000th of the angular resolution JWST achieves. Detection lies far beyond current capabilities, but undetectable does not mean non-existent. Every Saturn-like world we have ever studied closely hosts an extensive satellite system. There is no compelling physical reason why S1 should be different. The implications for astrobiology shift from theoretical interest to something more immediate when you consider what it would mean to have potentially habitable real estate 4 light-years from Earth. This is not a target at the center of the galaxy, inaccessible to any conceivable future technology. It is not a world orbiting a star 100 light-years distant, requiring journeys measured in centuries even at relativistic velocities. Alpha Centauri is close enough that visionary engineering concepts for interstellar probes, concepts that exist today and are being actively developed by research groups around the world, could reach it within a human lifetime. The Breakthrough Starshot initiative, announced in 2016 with the support of physicist Stephen Hawking and backed by substantial private funding, proposes accelerating gram-scale spacecraft to roughly 20% of the speed of light using arrays of ground-based lasers. At this velocity, such probes would require approximately 21 years to reach Alpha Centauri. Accounting for the time needed for return signals traveling at light speed, results could begin arriving on Earth within 25 to 26 years of launch, within a single human lifetime from mission initiation. Knowing that a gas giant orbits Alpha Centauri A's habitable zone and that this giant may host moons with liquid water on their surfaces transforms this engineering concept from elegant speculation into motivated mission planning. Scientists can specify what instruments such probes should carry. They can identify which wavelengths of reflected and emitted light would reveal the presence of oceans, atmospheres, or biological activity on any moons. They can design flyby trajectories that maximize the time available for observation of the most scientifically interesting targets. The detection of S1 focuses an otherwise abstract interstellar aspiration into something concrete. But the scientific significance of the Alpha Centauri observations extends well beyond the planet candidate itself. The same data that revealed S1 also produced what may be the most sensitive measurement of circumstellar dust ever obtained around any star other than the Sun. This measurement, though it received far less attention than the planetary detection in press coverage, represents a scientific achievement of comparable importance. Stars are not surrounded by empty space. Throughout their existence, planetary systems generate continuous streams of microscopic debris from collisions between asteroids, the sublimation of comets, and the slow erosion of smaller bodies by micrometeorite impacts. This dust pervades the inner planetary system, forming a diffuse cloud that scatters starlight and emits thermal radiation. In our own solar system, this zodiacal dust creates the faint glow visible along the ecliptic plane before dawn and after dusk on sufficiently dark nights, a subtle illumination that ancient astronomers noticed and named, but could not explain. Around other stars, this circumstellar dust is called exozodiacal dust. Its presence matters for planet hunters in two important ways. First, dense dust clouds emit light that can overwhelm or contaminate the faint signals from planetary companions, complicating or preventing detection. A system with extensive exozodiacal emission might hide its planets behind a veil of thermally glowing debris, regardless of how sensitive the telescope pointing at it happens to be. Second, the density and distribution of exozodiacal dust encodes information about the dynamical state of the planetary system. Dense dust typically indicates recent collisional events, ongoing bombardment from asteroid populations, or a system still in the process of dynamical settling after an unstable early period. Previous measurements of exozodiacal dust around other stars could only constrain emission to levels tens or hundreds of times brighter than the dust in our own solar system. The sensitivity required to measure dust at solar system levels, the faint threshold at which a mature, stable system like ours operates, lay beyond what any previous instrument could achieve for targets beyond our own sun. The JWST observations of Alpha Centauri A constrained any zodiacal dust around that star to levels only approximately 5 to 8 times brighter than our solar system's zodiacal cloud. This is the most sensitive exozodiacal dust measurement ever obtained around any star beyond the Sun. For the first time, astronomers can meaningfully compare another star's dust environment to what we observe in our own cosmic neighborhood, comparing like with like, rather than comparing our mature, quiet system to dramatically more active ones. The relatively low dust levels around Alpha Centauri A carry several important implications. Systems with dense debris disks typically indicate dynamical youth or ongoing instability. Collisions between large bodies, the kind that produce substantial debris, are most common during a system's early chaotic period when orbital architectures are still settling and bodies are still clearing their orbital neighborhoods through gravitational interactions and physical collision. A mature system that has reached dynamical equilibrium generates far less debris because most potential collision partners have already been swept up, ejected, or incorporated into larger bodies over billions of years. Finding that Alpha Centauri A's dust environment resembles our own solar system's suggests that the system has similarly reached a mature, settled state. The planet formation and early dynamical evolution that would have generated abundant debris appears to be long concluded. Whatever bombardment events might have threatened early biospheres, if any existed on smaller inner worlds, would have subsided billions of years ago. The system's current dust levels are consistent with the kind of stable, relatively quiet environment that Earth has enjoyed for most of the past several billion years, the stability that allowed complex life to evolve without being repeatedly reset by catastrophic impact events. This is encouraging news for habitability prospects. Dense exozodiacal emission around a star would raise concerns about ongoing bombardment that might sterilize planetary surfaces or destabilize atmospheric systems. The low levels around Alpha Centauri A suggest these concerns do not apply. Whatever worlds or moons exist in the system likely face an impact environment broadly comparable to what Earth experiences today, manageable background bombardment, rather than the violent early conditions that characterized the solar system's first billion years. Now consider what S1's existence, if confirmed, implies for stars throughout the galaxy. Approximately half of all sun-like stars in the Milky Way reside in binary or multiple stellar systems. This has long posed a challenge for planetary scientists because binary companions introduce gravitational perturbations that theoretical models consistently predict should interfere with planetary formation and survival. The disruptions are particularly severe in tight binary systems where the companion approaches close enough to the primary star to strip material from the protoplanetary disk before planets can fully assemble. Alpha Centauri is precisely such a tight binary. The two main stars approach within 11 astronomical units at their closest passage. Computer simulations of disk dynamics in this binary configuration consistently find that material beyond roughly 1 to 2 astronomical units from each star experiences strong gravitational perturbations from the companion. Disk material in these regions gets stirred, heated, and eventually dispersed before it can coalesce into planetary embryos. The models predict that planetary formation should be significantly suppressed or entirely prevented for planets at the distances where S1 appears to orbit. And yet S1 apparently exists. This single fact, if confirmed, requires planetary formation theorists to revise models that have been standard for decades. Either the models overestimate how destructive binary gravitational perturbations are during the disk phase, or some formation mechanism exists that current simulations fail to capture, or planets can migrate from safer inner regions where they initially formed to their current positions through processes that subsequent orbital evolution preserves against dynamical disruption. Each possibility has different implications for planetary populations throughout the galaxy. The most optimistic interpretation suggests that binary star systems are far more hospitable to planet formation than theoretical models predicted. If Alpha Centauri, one of the tightest and most dynamically challenging binaries in the solar neighborhood, can produce a Saturn-mass planet in its habitable zone, then binary systems throughout the Milky Way may routinely host planetary families that current formation theory would predict should not exist. Consider the numbers. The Milky Way contains roughly 200 billion stars. Approximately half, or 100 billion, reside in binary or multiple stellar systems. If even 10% of these binary systems host planets comparable to S1 in their habitable zones, that represents 10 billion potentially interesting worlds scattered throughout our galaxy. 10 billion targets, each with the potential to host satellite systems where habitable conditions might exist. 10 billion systems that previous theoretical pessimism about binary habitability would have dismissed. Adding binary star planets to galactic habitability estimates could dramatically increase the total count of potentially life-supporting environments. Statistical studies of exoplanets around single stars already suggest that habitable zone planets are common, perhaps existing around 1 in 5 sunlike stars. If binary stars match even a fraction of this frequency, the census of potentially habitable real estate in the Milky Way grows substantially. Life, if it exists anywhere beyond Earth, might be distributed not just around solitary stars, but throughout the much larger population of binary and multiple stellar systems as well. The constraints placed by the Alpha Centauri observations on planets not detected also carry information worth extracting. The sensitivity achieved during the August 2024 campaign was sufficient to detect any Jupiter mass or larger planet orbiting beyond approximately 2 astronomical units from Alpha Centauri A. No such detection was made except for S1 itself. This means the system's inner region, at least as probed by this observational campaign, does not contain additional gas giants at Jupiter mass or above in the surveyed zone. This null result matters for smaller worlds that remain completely beyond direct imaging detection limits. Gas giants exert gravitational influence on smaller companions that can disrupt their orbits through resonance interactions or close encounters. A system containing multiple massive gas giants leaves little dynamically stable space for the smaller rocky worlds that might support terrestrial biology. Finding only one modest gas giant in the Alpha Centauri A inner system leaves substantial orbital real estate potentially available for smaller companions. Earth-sized planets could orbit closer to the star within regions that the coronagraph cannot currently probe without gravitational harassment from additional giant companions. These smaller worlds, if they exist, remain far below any existing or near-future direct imaging detection threshold, but they might reveal themselves through complementary observation methods operating on different physical principles. Radial velocity surveys measuring the Doppler shift of stellar spectral lines as a planet's gravity tugs its host star toward and away from Earth could potentially detect Earth-mass companions in the inner system, given sufficient measurement precision and observational time baseline. Astrometric measurements tracking the star's position on the sky to sub-milliarc-second precision might detect the tiny wobbles induced by terrestrial mass companions over long baselines of observation. The Alpha Centauri system has been monitored by radial velocity spectrographs for decades. The data already constrains what can exist in the inner system without having been detected. Future instruments with improved precision will push these constraints further, combined with direct imaging constraints from JWST and eventually from next-generation ground-based telescopes. The accumulating data will progressively reveal the full planetary architecture of our nearest stellar neighborhood. What makes this process so different from planet-hunting campaigns around distant stars is precisely the proximity that makes observations so difficult. At 4.37 light-years, Alpha Centauri is close enough that the complementary observational methods reinforce each other in unusually powerful ways. A radial velocity detection of an inner rocky planet combined with a direct imaging detection of an outer gas giant would together constrain the system architecture with a detail impossible to achieve for stars hundreds of light-years away. An astrometric detection of orbital perturbations combined with direct imaging of S1 would reveal whether additional unseen companions influence S1's motion. The closeness that creates technical challenges for any single observational method becomes an advantage when multiple methods are combined. No other stellar system offers this combination of proximity, solar similarity, and potential habitability. The psychological dimension of this scientific story resists purely analytical treatment. Alpha Centauri occupies a unique position in human consciousness that extends beyond its astrophysical characteristics. It is the nearest star to our own sun. That simple fact has made it the default destination of human interstellar imagination since we first understood what stars are and how far away they sit. Science fiction writers placed alien civilizations there. Philosophers used its proximity to argue that interstellar travel was not merely theoretical fantasy, but a genuine long-term engineering challenge humanity might actually face. Engineers at institutes like Breakthrough Starshot pointed to Alpha Centauri specifically because its proximity made it, if not easy, at least conceivably reachable within timescales relevant to human planning. Now, for the first time, we have observational evidence suggesting that something actually orbits one of those stars. The question has moved from whether Alpha Centauri has planets to what those planets are like. The destination has revealed itself partially through a single faint detection that may or may not survive the scrutiny of additional observations. But the fact that we can ask the question at all, that we have developed instruments sensitive enough to detect a Saturn-mass world orbiting in the habitable zone of a star 4 light-years away, marks a genuine threshold in human capability. We are no longer merely imagining what might orbit. There is a number buried in the technical specifications of the August 2024 detection that deserves more attention than it typically receives in discussions of this discovery. The contrast ratio achieved during the S1 observation was approximately 10,000 to 1. Take a moment to feel the weight of that figure. JWST detected an object shining 10,000 times more faintly than the already suppressed residual glow of its host star after the coronagraph had already reduced Alpha Centauri A's blinding output by factors of hundreds through destructive interference. The raw brightness difference between Alpha Centauri A at full intensity and the planet candidate S1 is orders of magnitude larger still. What JWST accomplished in those August hours was not merely a planetary detection, it was a demonstration that human engineering had crossed a threshold that most astronomers, even optimistic ones, considered unreachable with current technology. To understand what this means, consider an analogy that brings the achievement into human scale. Imagine you are standing in Los Angeles on a clear night. Across the continent in New York City, someone has switched on a lighthouse. That lighthouse beam, visible from several miles at sea, blazes with intense white light. Now imagine that hovering beside the lighthouse, separated from the beam by no more than a few inches, is a single candle flame. Your task is to photograph that candle flame from Los Angeles without the lighthouse's glare washing it out entirely. The brightness difference between the lighthouse and the candle is less extreme than the brightness difference between Alpha Centauri A and S1. The angular separation between your objects is smaller. The atmospheric distortion between you and your target is real and constantly changing. This is roughly what JWST accomplished. The angular separation between S1 and its host star measured approximately 1.5 arcseconds during the August detection. To appreciate how small this angle is, hold your arm outstretched and look at your thumbnail. The angle subtended by your thumbnail nail from that distance is roughly 1 degree or 3600 arcseconds. The separation between S1 and Alpha Centauri A is 1.5 arcseconds. It is 1/400 of the angle your thumbnail subtends. At that angular separation, no previous direct imaging instrument had ever successfully detected a planetary companion around any star. Every other directly imaged exoplanet sits at angular separations of tens or hundreds of arcseconds from its host star, far enough from the stellar glare to emerge from coronagraphic suppression without requiring the extreme performance JWST demonstrated at Alpha Centauri. S1, if confirmed, would simultaneously claim multiple records that explain why the astronomical community continues to pursue this candidate, despite the uncertainty surrounding its existence. It would be the closest exoplanet to Earth orbiting within the temperate zone of a sun-like star. The planets around Proxima Centauri lie slightly closer in raw distance at 4.24 light-years versus 4.37, but they orbit a red dwarf star whose habitable zone, whose radiation, environment, and flare activity differ, so fundamentally from sun-like conditions that the comparison carries little astrobiological weight. A habitable zone planet around Alpha Centauri A would be something genuinely different. A world heated by sun-like radiation in a system whose architecture and age resemble our own solar neighborhood. It would be the nearest directly imaged exoplanet by a margin that renders all previous records almost quaint. The next closest directly imaged exoplanet candidates orbit host stars more than 10 times farther from Earth than Alpha Centauri. Most directly imaged worlds circle stellar furnaces located hundreds of light-years distant. The proximity that creates such observational difficulty simultaneously enables scientific opportunities completely inaccessible for more remote targets. It would be the oldest directly imaged exoplanet by an enormous factor. Current directly imaged planets almost universally orbit young stars associations less than 100 million years old, where formation heat makes planets dramatically easier to detect. Alpha Centauri A's age of approximately 5 billion years matches our own Sun's age almost exactly. S1 would be the first directly imaged mature planet, a world that has evolved for the same duration as Earth, rather than representing a planetary system still in its infancy. It would be the coldest directly imaged exoplanet by a substantial margin. The current catalogue of directly imaged worlds skews strongly toward hot, young, massive objects, precisely because their thermal emission is orders of magnitude more intense than mature, cool worlds. S1's effective temperature of approximately 225 Kelvin sits far below any previously imaged world. Its detection opens direct imaging to the cold planetary population that previous surveys could not reach, the population most relevant to understanding mature planetary systems like our own. It would be the closest to its host star of any directly imaged planet in angular separation terms. This record reflects both the technical achievement involved and the scientific significance of detecting planets in the inner system regions where habitable conditions exist, rather than in the cold outer reaches where formation models predict giant planets more commonly reside. Each of these superlatives reflects a genuine expansion of human observational capability, but the records themselves matter less than what they make possible. Superlatives are interesting in the moment of their establishment. What endures is what they enable. Consider what becomes scientifically feasible once a planet at this distance is confirmed and regularly observable. Atmospheric characterization of a mature gas giant becomes achievable for the first time. JWST carries spectroscopic instruments capable of dispersing incoming light into its component wavelengths and measuring brightness variations across the resulting spectrum with extraordinary precision. Different molecules absorb and emit radiation at characteristic wavelengths determined by their quantum mechanical properties, fingerprints, as distinctive as the patterns in a human iris. Methane absorbs strongly at 3.3 micrometers. Water vapor leaves signatures across multiple infrared bands. Ammonia, carbon dioxide, phosphine, and dozens of other compounds each impose their characteristic patterns on a planet's emerging spectrum. For S1, repeated spectroscopic observations across different orbital phases would reveal how atmospheric composition changes as the planet moves between perihelion and aphelion. Near perihelion, increased stellar heating drives molecules between different chemical states, pushing equilibrium toward higher temperature configurations that alter which compounds exist in which atmospheric layers. Near aphelion, cooling shifts these equilibria back toward lower temperature states. The spectral variations encode a wealth of information about vertical temperature, structure, cloud deck formation, and global atmospheric dynamics that single-epoch observations can never provide. No such data exists for any mature gas giant other than those in our solar system. Every other directly imaged exoplanet is too young and too hot, too dominated by formation heat, to serve as an analog for evolved planetary atmospheres. S1 would provide the first externally observed mature gas giant spectrum, a Rosetta Stone, for calibrating the atmospheric models that planetary scientists apply to Jupiter and Saturn, and then extrapolate to exoplanets around distant stars. The orbital dynamics themselves become measurable with progressively increasing precision as observations accumulate across years. Each new detection epoch constrains the allowed orbital parameter space, eliminating configurations inconsistent with the observed position and progressively converging toward the true orbital solution. Over a baseline of a decade or more, measurements of sufficient precision might detect subtle deviations from pure Keplerian motion, the small systematic residuals that would appear if unseen additional planets share the system and exert their gravitational influence on S1's observed path. These perturbations, if detected, would reveal hidden planetary companions entirely inaccessible to direct imaging. A super-Earth orbiting at 0.5 astronomical units from Alpha Centauri, afar inside the coronagraph's inner working angle and therefore invisible to current instruments, might nonetheless announce its existence through the tiny gravitational nudges it delivers to S1's orbit over decades of observation. Gravitational detection of invisible companions through their influence on visible ones is a technique with deep roots in astronomical history. The existence of Neptune was inferred from irregularities in Uranus's orbit before any telescope had ever directly observed the outer ice giant. The same principle could reveal terrestrial companions orbiting Alpha Centauri A within the zone where direct imaging will remain impossible for years to come. The long-term orbital evolution of S1 itself provides tests of theoretical stability models. The unusual orbital inclination relative to the binary plane should produce measurable precession over timescales of decades to centuries, as gravitational torques from Alpha Centauri B slowly rotate the orbital perihelion direction. Detecting this precession would confirm that the orbit is evolving under exactly the dynamical influences theory predicts, strengthening confidence in models of how planetary systems survive within binary stellar environments. Unexpected deviations from predicted precession rates would indicate additional dynamical influences not yet accounted for in the models pointing toward new physics or undiscovered system members. But to do any of this science, the planet must first be confirmed, and confirmation requires the 2026 observation. The orbital models that emerged from combining the 2019 ground-based detection, the 2024 JWST detection, and the 2025 non-detections converge on a prediction. Based on the family of gravitationally stable orbits, consistent with all available data, S1 should be approaching aphelion again sometime in mid-2026. The planet's eccentric path should carry it back toward the 2 astronomical unit separation where Miri achieves sufficient sensitivity for detection. The most probable window for reobservation centers on August 2026, creating a neat symmetry with the original August 2024 discovery. This prediction is not guaranteed. The orbital constraints remain wide enough that some allowed configurations would keep S1 in the coronagraphic blind zone through 2026 and into 2027. Others would bring it to favorable positions as early as spring 2026. The August window represents the peak of the predicted probability distribution rather than a certainty, but it represents the best available target for the follow-up campaign that will either confirm S1's existence or force a fundamental reassessment of what was detected 2 years earlier. The Space Telescope Science Institute, which manages JWST operations, has already received requests for observation time during this window. The scientific justification is straightforward. No other target in the observable universe offers comparable scientific return per photon collected. A confirmed planetary companion orbiting Alpha Centauri A at 2 astronomical units would generate decades of follow-up research across multiple disciplines: atmospheric science, orbital dynamics, planetary formation theory, astrobiology, and interstellar mission planning simultaneously. The opportunity cost of not observing during the predicted window is essentially incalculable. The astronomical community watches the countdown with an anticipation that has no recent precedent. And while that anticipation builds the broader question that S1's detection raises, deserves careful examination. Because the significance of finding planets around our nearest sun-like neighbor extends far beyond the specific scientific measurements that confirmation would enable. It touches on questions that scientists have been trying to quantify for more than 6 decades, questions that remain among the most important unanswered problems in all of human intellectual history. In 1961, the astronomer Frank Drake sat down before a gathering of scientists at the National Radio Astronomy Observatory in Greenbank, West Virginia, and wrote an equation on a blackboard. The equation was not a new physical law. It was not a mathematical derivation of some previously unknown relationship between measurable quantities. It was instead a framework for organizing ignorance, a way of breaking a vast and otherwise paralyzing question into smaller components that science might, in principle, answer one by one. The question the Drake equation addresses is whether technological civilizations exist elsewhere in the galaxy. The equation multiplies together a series of factors: the rate at which stars form in the Milky Way, the fraction of those stars that host planets, the fraction of planetary systems that include worlds capable of supporting life, the fraction of such worlds where life actually emerges, the fraction of living worlds where intelligence develops, the fraction of intelligent species that develop communicable technology, and finally, the average duration over which such civilizations remain detectable. Multiply these factors together, and the result estimates how many technological civilizations might exist in our galaxy at any given moment. When Drake wrote the equation in 1961, almost every factor in it was completely unknown. Scientists had not yet confirmed the existence of any planets around any star other than our own sun. The question of whether planetary systems were common or rare had no observational answer. Some theoretical models suggested planetary formation was a natural and frequent consequence of stellar birth. Others argued that the specific conditions required for planet formation were unusual enough that most stars spent their lives alone, without companions of any kind. The decades that followed progressively filled in the equation's terms. The discovery of the first confirmed exoplanet around a sun-like star in 199551 Pegasi b, detected through radial velocity measurements by Michel Mayor and Didier Queloz, opened a door that has never closed. In the years since, the catalogue of confirmed exoplanets has grown to nearly 6,000 worlds, orbiting hundreds of different stellar types at every conceivable distance. The Kepler Space Telescope alone surveyed more than 1,500,000 stars, and found that planetary systems are not exceptional but routine. Statistical analysis of Kepler's results suggests that the average star in the Milky Way hosts at least one planet. Planets are everywhere. The Drake equation term representing planetary frequency approaches 1. But knowing that planets are common tells us almost nothing about whether life is common. The jump from abundant planets to abundant life requires answering a question that has only one data point: Earth. We know that life emerged on at least one planet in the galaxy. We do not know whether that emergence was inevitable, given suitable conditions, have probable, but not certain, rare, but not unique, or an event of such improbable coincidence that it may have occurred only once in the observable universe. That single data point haunts every discussion of extraterrestrial life, with an ambiguity that more planets cannot resolve. Finding a second example of life anywhere in any form would be the most important scientific discovery in human history. It would transform the question of life's cosmic frequency from a problem with one data point to a problem with two. From that second data point, statistical inference could begin in earnest. And this is why finding planets around Alpha Centauri matters to astrobiologists with an urgency that pure astronomical interest alone cannot explain. Alpha Centauri is the one stellar system close enough that probes launched with foreseeable technology might actually arrive and return data within human timescales. The proximity that makes observation so challenging is simultaneously what makes the system so uniquely valuable for the long-term question of whether life exists beyond Earth. Every other potentially interesting stellar system requires travel times measured in centuries or millennia, even at the most optimistic projections for future propulsion technology. Alpha Centauri requires only decades. If S1 hosts moons with liquid water on their surfaces, if chemistry has had 5 billion years to evolve in those liquid water environments heated by a sun-like star, then life might exist there. Not certainly. Not even probably, given our profound uncertainty about how life's emergence scales with opportunity, but possibly. And possibly in a system 4 light-years away is a different kind of possibility than possibly in a system 100 light-years distant, or 1,000,000 light-years distant. The breakthrough starshot concept targets Alpha Centauri specifically because of this proximity. The plan involves using ground-based laser arrays, potentially containing thousands of individual laser units focused on a common point, to accelerate tiny spacecraft carrying cameras, communication systems, and basic scientific instruments to velocities approaching 20% of the speed of light. At that velocity, the probes would reach Alpha Centauri in approximately 21 years after launch. Signals from the probes traveling at the speed of light would require an additional 4.37 years to return to Earth. Total round-trip time from launch to first data, roughly 25 to 26 years. Within a human lifetime, the technical challenges confronting this concept are enormous. Accelerating gram-scale spacecraft to relativistic velocities requires laser power densities that do not yet exist. Pointing the laser array at a target with sufficient precision over the acceleration phase demands engineering solutions that have not yet been demonstrated. Surviving the interstellar medium, which contains enough dust and gas to present real hazards to craft traveling at 20% of light speed, requires shielding approaches still under development. Communicating results from 4 light-years away with the power budgets available to gram-scale spacecraft presents communication engineering challenges of a difficulty without precedent. But none of these challenges violates physical laws. All of them are engineering problems rather than impossibilities. And the difference between an engineering problem and a physical impossibility is the difference between a challenge that human ingenuity might eventually overcome and a barrier that admits no solution regardless of how clever or persistent the attempt. Knowing that something orbits Alpha Centauri A does not make breakthrough starshot easier to build, but it changes the nature of what the mission is for. A probe sent to Alpha Centauri without any knowledge of what awaits it would be exploring, in the most fundamental sense, traveling toward an unknown destination to discover what exists there. A probe sent with knowledge that a gas giant orbits in the habitable zone, potentially hosting moons with liquid water, has a specific target and specific questions to answer. The mission planning changes, the instrument choices change, the public and institutional motivation changes. The difference between exploring an unknown destination and investigating a known one is the difference between Columbus sailing west without maps and a modern expedition traveling to a geographic feature identified by satellite imagery. Both involve journeys. Both require courage and resources and technical skill, but one proceeds blindly while the other proceeds with purpose. S1 gives breakthrough starshot purpose. Meanwhile, closer to home, The next generation of astronomical instruments is assembling itself on mountaintops and in the minds of engineers, with growing confidence that the universe is about to reveal itself in unprecedented detail. The extremely large telescope currently under construction on Cerro Armazones in Chile's Atacama Desert will, when it achieves first light, sometime before 2030, possess a primary mirror 39 meters in diameter. This figure requires a moment of context. The largest existing optical telescopes on Earth have primary mirrors roughly 10 meters across. JWST's primary mirror spans 6.5 meters. The ELT's 39-meter mirror will gather more light than all existing large optical telescopes combined. Its adaptive optics systems, which measure and correct atmospheric distortion in real time using networks of actuators that reshape mirror segments thousands of times per second, will achieve angular resolution that surpasses space-based observatories despite the turbulent atmosphere between the telescope and its targets. The ELT's coronagraphic instruments will push contrast ratios and inner working angles well beyond what JWST demonstrated during the Alpha Centauri observations. Planets currently hidden in stellar glare that MIRI could not penetrate will become detectable. Atmospheric spectra currently too faint to measure with any existing instrument will yield chemical compositions. The Alpha Centauri system that JWST could only barely probe at the limits of its capability will become a target for detailed, systematic characterization. The 30-meter telescope planned for Mauna Kea in Hawaii offers similar capabilities from a different geographical location, enabling continuous monitoring of interesting targets across the calendar year, regardless of weather interruptions at any single site. The giant Magellan telescope under construction at Las Campanas Observatory in Chile combines 7, 8, 4-meter mirrors into a coherent array with 2 5-meter equivalent aperture. Each facility represents a quantum leap in observational capability. Together, they constitute a revolution. Within 15 years, these instruments will observe Alpha Centauri, with sensitivity exceeding JWST's current performance by substantial margins. If S1 is real and follows the orbital family derived from current constraints, the ELT's coronagraphic instruments will track its position with sub-milliarc-second precision across years of observation, refining the orbital solution to a degree that will either reveal additional unseen companions through their gravitational fingerprints or confirm that S1 travels alone through the Alpha Centauri A inner system. If additional planets exist at smaller separations or lower masses than JWST could detect, the new ground-based facilities will find them. The Nancy Grace Roman Space Telescope, entering final phases of preparation for launch in the mid-2020s, includes a coronagraph technology demonstration that will test starlight suppression techniques beyond any current operational space-based system. Roman's primary science program involves wide-field surveys of the galaxy's stellar populations rather than targeted exoplanet characterization, but its coronagraph will prove concepts essential for subsequent dedicated missions. Each generation of instrument development inherits lessons from its predecessors and extends the boundary of achievable sensitivity by increments that accumulate into transformations. Further in the future, the Habitable Worlds Observatory concept represents the astronomical community's consensus choice for the next major space telescope following JWST's eventual operational lifetime. This mission, recommended by the most recent Astronomy and Astrophysics Decadal Survey, would be specifically designed to directly image Earth-like planets around nearby stars and search their atmospheres for biosignature gases, molecules whose presence in combination cannot be explained by purely geological or chemical processes, and therefore indicates biological activity. Oxygen alone does not constitute a biosignature. It can be produced abiotically through photochemical processes. But oxygen combined with methane, which react chemically, and should not coexist in significant quantities without continuous replenishment, represents a combination that biology maintains on Earth, and that purely physical chemistry can sustain. Finding this combination, or similar unlikely coexistences of reactive molecules, in the atmosphere of an exoplanet would constitute the strongest possible evidence for extraterrestrial life, detectable without physically visiting the target world. The technology pathfinder observations achieved at Alpha Centauri directly inform the Habitable Worlds Observatory's design. The contrast ratios demonstrated the angular separations accessed the systematic noise sources encountered and characterized. All provide real-world engineering data for teams working on next-generation instruments. The Alpha Centauri success demonstrates that coronagraphic suppression at the levels required for Earth-sized planet detection is achievable in principle, even when the target star is far brighter and closer than anything the Habitable Worlds Observatory will need to handle. Progress cascades forward from each achieved milestone. But these telescopes, magnificent as they will be, cannot answer the fundamental question that Alpha Centauri's planetary system poses in its most profound form. They can tell us what orbits the nearest star. They can characterize atmospheres, measure temperatures, map brightness distributions, detect chemical signatures. They can determine whether moons exist around S1, what those moons look like from a distance, whether their spectra contain the fingerprints of liquid water or biological chemistry. What they cannot do is visit. The difference between remote observation and physical presence matters in ways that are difficult to fully articulate, but easy to feel. We have observed the moon from Earth for all of human history. We characterized its surface through centuries of increasingly powerful telescopes. We knew its size, its distance, its basic geology, its lack of substantial atmosphere. And then 12 human beings walked on it between 1969 and 1972. And what we learned from those visits, from the samples brought back from the instruments left behind, from the simple fact of human presence in that alien environment, exceeded in certain dimensions. Everything accumulated through all the preceding centuries of remote observation. There are things you can only learn by going. Alpha Centauri is 4 light-years away. No technology available now, or likely available within the next century, will carry human beings across that distance within a human lifetime. But machines, tiny ones traveling at relativistic speeds, might make that journey within decades of launch, and the scientific questions those machines could answer. Questions about habitability, about chemistry, about whether life has independently emerged in our nearest stellar neighborhood, might transform our understanding of life's place in the universe in ways that no amount of telescope observation from Earth can match. The detection of S1 has made those questions specific rather than abstract. It has turned a philosophical inquiry about whether interesting things exist around Alpha Centauri into an engineering challenge about how to investigate specific interesting things that appear to actually be there. That transformation is not trivial. It is the difference between wondering and knowing what you are wondering about. The universe responds to specific questions more readily than to vague ones. Science advances most powerfully when it has targets, when the next observation is motivated by a specific prediction from a specific model rather than a general hope that something interesting might appear. S1 has given the next generation of astronomers and engineers a specific target, a specific prediction, and a specific date to aim toward. August 2026 approaches. The universe already knows what JWST will find when it turns its golden mirrors toward Alpha Centauri A during that predicted window. The planet either exists along one of the allowed orbital paths waiting to emerge from its coronagraphic blind zone at the predicted moment, or the August 2024 detection was something other than a planet, a statistical fluctuation, a background source, an instrumental artifact that somehow survived every test designed to catch it. One of these things is true. The universe has already made its decision. We are simply waiting for the light to arrive and tell us what that decision was. There is a thought experiment worth sitting with before we arrive at the end of this story. Imagine that you could travel backward in time, not to any particular historical moment, not to witness any specific event, but simply to find a human being living at some point before the invention of the telescope, before Galileo turned his crude optical instrument toward the night sky in 1609 and discovered that the smooth, luminous face of the moon was actually a landscape of mountains and craters. before any person alive had any means of knowing that the points of light scattered across the darkness above them were anything other than what they appeared to be, lights, fixed in the heavenly sphere, eternal and unchanging, and fundamentally different in nature from the terrestrial world where human lives unfolded. Find that person, sit beside them on a clear night, point toward the brightest star visible in the southern sky, and tell them what you know. Tell them that the light touching their eyes right now left its source 4 years and 4 months ago, traveling at 186,000 miles per second across a void, so empty that the word emptiness does not begin to capture its character. Tell them that the source of that light is a nuclear furnace containing more than 1 million times the mass of the Earth, burning at nearly 6,000 degrees on its surface and tens of millions of degrees in its core, sustained by the fusion of hydrogen into helium at a rate that releases more energy every second than humanity has consumed in all of recorded history combined. Tell them that this furnace is not alone, that it dances in a slow gravitational embrace with a companion star, that a third dim ember lurks at the edge of the system, and that circling somewhere in the warmth of the largest star, a world of swirling clouds and crushing pressure, roughly the mass of Saturn, traces an eccentric ellipse that carries it through the zone where liquid water is thermodynamically possible. Tell them that we know all of this, that we measured it, that we built an instrument the size of a tennis court, folded it into a rocket, and launched it 1 million miles from Earth, unfolded it in the cold darkness of interplanetary space, and pointed it at a star so bright it could damage the sensitive detectors looking at it, and found in the processed data that came back a faint point of light that may be a world. The person beside you would have no framework for any of this, not the nuclear physics, not the light years, not the coronagraph or the Lagrange point or the principal component analysis. But they would understand one thing, perhaps the most important thing, without needing any of the technical vocabulary. They would understand that you had looked at something impossibly far away and seen it. That is what science is at its deepest level. It is the extension of human sight beyond the boundaries that biology imposed on us. It is the refusal to accept that the limits of the naked eye are the limits of what can be known. Every instrument ever built, from Galileo's lens to JWST's golden mirrors, is an argument against the proposition that the universe is too large and too remote for creatures like us to understand. Each one says, in the language of metal and glass and quantum electronics, not yet. We can see further than this. Alpha Centauri has been visible to human eyes for as long as human eyes have existed to see it. Our ancestors in the southern hemisphere looked up at this brilliant point and wove it into their understanding of the sky. Pacific navigators used it to chart courses across open ocean. Ancient peoples told stories about it, incorporated it into cosmologies that made the night sky legible and meaningful. The star has been present in human consciousness in one form or another for the entire duration of our species' existence on this planet. For all of that time, we did not know what it was. We knew it shone. We knew it rose and set with the seasons. We knew it could be used to find direction in the dark. But we did not know it was a sun. We did not know that the light reaching our eyes had departed a stellar furnace burning with the same nuclear fire as our own sun. We did not know it was part of a triple stellar system, that 2 sun-like stars danced around each other in an 80-year orbital waltz, while a third dim companion lurked at the edge of the family. We did not know any of this because knowing it required tools we had not yet built. The history of what we have learned about Alpha Centauri is a compressed history of human astronomical ambition. Each generation of instruments revealed a new layer of the system's nature. The telescope revealed its brilliance as the third brightest star in the sky. The spectroscope revealed its temperature and composition, confirming it as a solar analog. Precision astrometry revealed its distance, placing it definitively at the nearest edge of our stellar neighborhood. Radial velocity surveys constrained what massive planets could exist without detection. And now JWST in August of 2024 detected something beside Alpha Centauri A that previous instruments could not see. Each revelation built on what came before. Each tool opened questions the previous tool could not answer. This is not a coincidence. It is the structure of scientific progress. Every answered question exposes the architecture of the next unanswered one. Every instrument designed to see further reveals, by seeing further, how much further there is still to see. The August 2024 detection sits at the current frontier of this long progression. It is the latest answer to a question that humanity has been asking in different forms and with increasingly powerful means for centuries. Does something orbit our nearest sun-like stellar neighbor? The answer appears to be yes, provisionally, subject to confirmation, dependent on what the 2026 observations reveal. But even as a provisional answer, it changes something. The universe is not the same place it was before August 2024. Not physically, of course. Alpha Centauri A has not changed. S1, if it exists, has been tracing its eccentric ellipse for 5 billion years, without any awareness of whether creatures on a small rocky world 4 light-years away had yet developed instruments capable of detecting it. The cosmos proceeds according to its own indifferent schedule, regardless of what human beings manage to observe or fail to observe. What changed was our knowledge of it, and knowledge, while it does not alter the physical universe, alters irreversibly the relationship between human consciousness and the cosmos that contains it. We cannot unknow what we have learned. We cannot return to the period before 51 Pegasi b was discovered and recover the uncertainty about whether planets existed around other stars. We cannot recover the pre-Copernican conviction that Earth occupies the center of creation. Each piece of knowledge, once genuinely acquired, becomes part of the foundation on which all subsequent understanding is built. The provisional knowledge that a Saturn-mass world may orbit Alpha Centauri A's habitable zone is now part of that foundation. Even if 2026 observations fail to confirm S1 and the candidate is eventually withdrawn, the knowledge that JWST can achieve the contrast ratios and angular separations required to detect such objects remains. The techniques developed for this impossible observation, the blind offset procedure, the reference star, differential imaging, the specialized noise reduction algorithms, all of these represent genuine additions to human capability that will not be forgotten. But consider for a moment the possibility that 2026 does confirm S1. Consider what it would mean to stand outside on a clear night face, the constellation Centaurus blazing in the southern sky, and know with genuine scientific confidence that the brilliant point of light called Alpha Centauri contains, among its 3 stellar members, at least one planet. That somewhere in the warmth of the largest star, a world of swirling clouds circles in an eccentric ellipse, passing through the zone where liquid water is possible, perhaps hosting moons where something more complex than chemistry has taken hold over the 5 billion years since the system formed. We cannot see those moons, we cannot resolve them, we cannot detect their atmospheres or their surfaces or whatever might move across them if anything does. 4 light-years is close enough to detect a Saturn-mass planet under the most favorable observational conditions with the most powerful telescope ever built. It is not close enough with any existing or near-future technology to observe a moon orbiting that planet, much less any surface feature of such a moon. But we can know they might be there, and knowing they might be there in a place that future technology might actually reach in a system that a probe launched within the next few decades might actually visit and report back from within a human lifetime is a different kind of knowing than the abstract statistical knowledge that habitable worlds probably exist somewhere in the galaxy. Statistical knowledge tells you that something is likely somewhere. Physical proximity tells you that something might be there specifically in that direction around that star, waiting in the dark and the warmth for whatever finds it first. Proximity collapses abstraction into specificity. It turns probably somewhere into possibly there. The 4 light-years separating Earth from Alpha Centauri will not shrink. The distance is what it is fixed by the positions of 2 stellar systems in a galaxy that does not consult human preferences when it arranges its contents. But our relationship to that distance is not fixed. It changes with every new capability we develop, every instrument we build, every probe we design and launch and send outward from this planet into the darkness between the stars. The first generation of humans who understood that stars were distant suns looked at Alpha Centauri and could do nothing more than look. The generation that built the first telescopes could resolve it from its companion and measure its parallax. The generation that built spectroscopes could measure its temperature and composition. The generation that built precision radial velocity spectrographs could constrain what massive planets did not orbit it. The generation that built and launched and operated the James Webb Space Telescope found something that might be a world. The generation that builds the extremely large telescope will characterize whatever worlds are found there. The generation that engineers the first relativistic probes might send them. The generation that receives the data from those probes might know for the first time in the history of our species whether the nearest sun-like star to our own sun is home to life. We are somewhere in this sequence. We are not at the beginning where Alpha Centauri was merely a light. We are not at the end where its worlds and whatever inhabits them might be known. We are in the middle at the precise moment when the light from a possible planet arrived at our instruments and we had barely just enough technology to catch it. This is where we are, at the edge of the visible, at the threshold where distant things begin to yield their secrets to patient observers willing to push instruments beyond their designed limits and ask questions that previous generations lacked the tools to even formulate precisely. The questions ahead are vast. They dwarf what we currently know, the way the ocean dwarfs a tide pool. We do not know whether S1 is real. We do not know whether it hosts moons. We do not know whether those moons are habitable. We do not know whether life has emerged anywhere in the Alpha Centauri system. We do not know whether life exists anywhere in the universe other than on the pale blue world we inhabit. We do not know whether intelligence has arisen elsewhere, whether consciousness has looked out at the same stars from other eyes on other worlds and wondered the same things we wonder about the darkness above. We do not know any of this, but we are learning. The instrument that detected S1 for all its extraordinary capability represents one step in a progression that has been accumulating for 4 centuries and shows no sign of slowing. The next step is already under construction in the Atacama Desert, where the skeleton of the extremely large telescope rises from the rock of a mountain that will not exist in its current form 100 years from now, because the telescope being built upon it will have worn it down through the patient, mechanical settling of enormous instruments on ancient stone. After that step will come another and another, each one seeing further, each one asking questions the previous one could not formulate because it could not see far enough to know they needed asking. This is how it works. This is how it has always worked from the moment the first human being looked up and wondered whether the lights in the sky were close or far familiar, or alien alone or accompanied. The wondering does not stop. It cannot stop because every answer breeds questions the way every horizon, when reached, reveals another horizon beyond it. The universe is not running out of secrets to yield. It is running out of nothing. It is inexhaustible in its depth and in the questions it poses to any mind willing to look carefully enough at what it contains. Alpha Centauri ablaze in the southern sky tonight. Its light departing that stellar furnace 4 years and 4 months ago is arriving at your eyes right now as you read these words. Perhaps somewhere in that same system, carried on infrared photons too faint for any naked eye to detect, is the thermal glow of a Saturn-mass world tracing its eccentric ellipse through the habitable zone of our nearest sun-like stellar neighbor. The light is already here. We built something extraordinary enough to catch a whisper of it in August 2024. We watched that whisper disappear in the months that followed, not because it was never real, but because the planet may have moved to a place our instruments cannot yet follow. We are building better instruments. We are planning the observations that will either confirm what we found or reveal that we must look again with different eyes. And somewhere in this quiet interval between detection and confirmation, between the first glimpse and the eventual knowledge, humanity occupies a position that no generation before us has ever occupied and that no generation after us ever occupy again. The position of being the first to have looked at our nearest sun-like stellar neighbor and seen, however faintly, however provisionally, however much in need of verification, something that might be a world. The stars are not impossibly distant. They merely wait for us to develop the means to reach them first, with light, then with instruments that catch that light, then perhaps with machines that cross the darkness and return with answers, and eventually, if our curiosity and our patience and our capacity for wonder prove sufficient with something more. A faint point of thermal emission shines beside Alpha Centauri A, or it does not. The universe already knows which is true. We are still learning to ask the question clearly enough to hear the answer. And that asking, that patient, persistent, unglamorous, magnificent asking, is the most extraordinary thing our species has ever done.